students! Welcome back to our educational videos on Form 5 Physics. Today's topic is Electromagnetism Part 1. This video is brought to you by our team Monyet Science, and let's enjoy the video. A brief outline of this video. We are going to explain about the definition of electromagnetism, application of electromagnetism, theories and laws of electromagnetism, and continue with magnetic effect of current carrying conductor and force on current carrying conductor in magnetic fields. First of all, what is electromagnetism? Electromagnetism is a phenomenon when current passes through a conductor. A magnetic field will be generated around the conductor and the conductor becomes a magnet. Next is the application of electromagnetism in our daily lives. This figure is showing the construction of an electric bell using electromagnets. When the switch is on, the circuit is completed and the current flows. The electromagnet becomes magnetized and hence attracts the soft iron armature and at the same time pulls the hammer to strike the gong. As soon as the hammer moves towards the gong, the circuit is broken. The current stops flowing and the electromagnet loses its magnetism. This causes the spring to pull back on the armature and reconnect the circuit again. When the circuit is connected, the electromagnet regains its magnetism and pulls on the armature, and hence the hammer is striking the gong again. This cycle repeats and the bell rings continuously. Furthermore, an electromagnetic relay can be built from electromagnets. A relay is an electrical switch that opens and closes under the control of another electrical circuit. The switch is operated by an electromagnet to open or close one of many sets of contacts. A relay has at least two circuits. One circuit can be used to control another circuit. The first circuit, the input circuit, supplies current to the electromagnet. When the circuit is closed, the electromagnet is magnetized and attracts one end of the iron armature. The armature then closes the second switch and allows the current flow into the second circuit. When the first switch is opened again, the current to the electromagnet is cut. The electromagnet loses its magnetism and the second switch is opened. Thus, the current stops to flow in the second circuit. Moreover, electromagnets can be used in a circuit breaker. This figure shows the structure of a circuit breaker. A circuit breaker is an automatic switch that cuts off current in a circuit when the current becomes too large. When the current in a circuit increases, the strength of the electromagnet will increase in accordance. This will put the soft iron armature towards the electromagnet. As a result, the spring pulls apart the contact and disconnects the circuit immediately, and the current stops the flow. We can reconnect the circuit by pressing the reset button. The reset button can be pushed to bring the contact back to its original position to reconnect the circuit. In addition, the construction of an earpiece is involved with electromagnets as well. When you speak to a friend through the telephone, your sound will be converted into an electric current by the mouthpiece of the telephone. The current produced is a varying current and the frequency of the current will be the same as the frequency of your sound. The current will be sent to the earpiece of the telephone of your friend. When the current passes through the solenoid, the iron core is magnetized. The strength of the magnetic field changes according to the varying current. When the current is high, the magnetic field will become stronger, and when the current is low, the magnetic field will become weaker. The soft iron diaphragm is pulled by the electromagnet and vibrates at the frequency of the varying current. The air around the diaphragm is stretched and compressed and produces a sound wave. The frequency of the sound produced in the telephone earpiece will be the same as your sound. Moving on to the next part, we are going to explain the theories and laws of electromagnetism. The first law in this chapter is Faraday's law. The magnitude of the induced EMF can be determined from Faraday's law, which is the equation above. N is the number of loops, delta phi is the change in magnetic flux, and delta t is the change in time. Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux through a coil, or alternatively, the rate of magnetic flux being cut. Therefore, the induced electromotive force, EMF, can be increased by using a stronger magnet, increasing the speed of relative motion, and increasing the number of turns of the coil. Next is Lenz's law. Lenz's law is reflected in the formula of Faraday's law, with the contribution of negative signs, which shows the expression below. When a magnet is moved into and out of a coil, the induced current that flows through the coil can be determined from Lenz's law. Lenz's law states that the induced current always flows in the direction that opposes the change in magnetic flux. Lenz's law also obeys the principle of conservation of energy. Work is done to move the magnet against the repulsive force. This work done is converted into electric energy, which manifests as an induced current. For a conductor in a closed circuit moving perpendicular to a magnetic field, the direction of induced current is determined from Fleming's right-hand rule. Fleming's right-hand rule is used to determine the direction of the induced current that flows from the wire when there is a relative motion with respect to the magnetic field. Moving on to the next section, we will investigate the magnetic effect of a current-carrying conductor. First of all, what is an electromagnet? An electromagnet can be made by sending a current through a coil of wire wounded around an iron core. Here is a demonstration of a simple electromagnet. When a current flows through a coil, it produces a magnetic field. The soft iron core becomes temporarily magnetized when the current is switched on. When the current is switched off, it loses its magnetism. By definition, the magnetic field pattern can be represented by field lines that show the shape of the field. Magnetic field lines which are close together represent a stronger field. The field direction is defined as the direction indicated by a compass needle placed in the magnetic field. To determine the direction of magnetic field around a current-carrying wire, right-hand grip rule is applied. Based on this figure, we imagine gripping the wire using your right hand, with your thumb pointing in the direction of current. Your other fingers now represent the direction of magnetic field. When the direction of the current is reversed, the magnetic field direction is also reversed. For the next subtopic, we are going to examine what happens to a current-carrying conductor in a magnetic field. An electric current produces a magnetic field around the wire. When a wire carries an electric current through another magnetic field, a force is exerted on the wire. The magnetic force on a current-carrying conductor in a magnetic field is due to the combination of magnetic field in the conductor and the external magnetic field to produce a resultant magnetic field. To determine the direction of magnetic force F acting on the wire, we can apply the concept of Fleming's left-hand rule. So basically, what is Fleming's left-hand rule? Fleming's left-hand rule is a simple and accurate way to find the direction of force or motion of the conductor in an electric motor when the magnetic field direction and the current direction are known. According to this diagram, the forefinger, second finger, and the thumb of the left hand are extended at right angles to each other, with the forefinger in the direction of the magnetic field, the second finger in the direction of the current, and the thumb will point in the direction of the force or motion. Now we are going to learn how a current-carrying conductor in a magnetic field experiences a force. In this case, we are using a permanent magnet and a current-carrying conductor to examine the magnetic force. The magnet or magnet produces a uniform parallel magnetic field, and the current-carrying vertical wire produces a circular magnetic field around itself. The wire is placed in the middle of the magnet or magnet, and the two fields interact to produce a resultant magnetic field known as the catapult field. At the upper region, the two fields are in the same direction, and they produce a stronger combined. At the lower region, the two fields act in opposite directions, and the combined field is weaker. The wire carrying a current thus experiences a resultant force in the direction from the stronger to the weaker field. This means in a downward direction. Therefore, the magnitude of the force on a current-carrying conductor in a magnetic field depends on the size of the current in the conductor and the strength of the magnetic field. Construction of a DC motor. Next, we will have a look on the working principle of a DC motor. A DC motor consists of a communicator which reverses the direction of current in the coil every half rotation so that the coil continues to turn in the same direction. A pair of carbon brush which contacts with the communicators to allow the current from the battery to enter the coil, and springs which functions to push the brush so that it is always in contact with the communicator. Working principle of DC motors. When current flows through the horizontal coil, magnetic field is produced around it. The interaction between the magnetic field of the current and the magnetic field of the permanent magnet produces a catapult field and two turning forces. The direction of the force is determined by Fleming's left-hand rule. The two forces produce a couple which rotates the coil. When the coil gets to the upright position, the contact between the carbon brushes with the communicator is broken. There is no turning force on it because no current flows in the coil, but the coil continues to rotate because of its inertia. When the coil is in a horizontal position again, the sides of the coil changes position. The communicator reverses the direction of the current in the coil to ensure that the forces on the coil turn the coil in one direction only. Therefore, the coil is still rotating in the same direction. The above processes are repeated and the motor continues to rotate. Last but not least, there are some factors that will affect the speed of rotation of the DC motor. For instance, the size of the current, the strength of the magnetic field of the magnet, the number of turns, and the area of the coil. That's all for our first part of electromagnetism, and stay tuned for part 2. See you!